Did you guys get it?
It is recording, right?
Yeah. Cool.
Alright. Well,
You guys have so much time to do this when you're sitting here. Bro,
Sorry. I didn't realize.
It's always
Oh.
right here.
It's okay. Don't worry about it.
But you know, this is not
meant to be.
alright. Let's hope you guys are hyped for designing your mouse. I know, it's pretty quick. You guys aren't even completely done with your route yet, but we're going to talk about designing your mouse already. Don't worry about it. So yeah, first off, in our design lecture, we're going to talk you through on how to navigate Digikey and other similar sites. Because you guys will need to do some part packing. That's part of the assignment. And filters on the pages, filtering from different parts, from different values of parts and all that, will be your best friend with this. And we'll give you a recommended parts list so you guys aren't completely in the blind in terms of what you need and how many you need, but you will have to go find them yourselves. Like, we can't just say, oh, everyone grab this specific size of a capacitor. What if you wanted to go smaller? We're giving you the freedom to do that. Yeah.
Oh, also, for this recommended parts list, we will have, it'll be like mainly the big parts, like with like the motor drivers, the power, the linear voltage regulators, the IR emitters and receivers. But then we expect you to like find passives and like other things in between on your own.
Yeah, and you can get pretty fine-tuned results from your parts within these filters. I believe in the earlier assignment we've had let you guys do a little bit of that on your own in 1A. Well, this time you will be really taking advantage of all these filters. Like, you could be picky with the manufacturer, what packaging size, and just all the other factors. And one cool thing about Digikey and several other sites like these, actually towards the bottom of a page, like say, oh, you looked at this capacitor, you want to get more that are similar brands, like similar specs, but just with different values. Well, you can actually scroll down. You can select all the attributes you want, and you can actually filter through to find similar products as this. So it will be really helpful for allowing your passives and all that. And some of the other sites, because sometimes you just run out of parts, sometimes it's just not stocked on Digikey. Mouser, Adafruit, SparkFun, Mouser, in terms of what their stock includes, it's pretty similar to Digikey. They might have some parts that are specialized that aren't on Digikey. Adafruit and SparkFun, in my opinion, have more diverse collection of parts. Like, you won't be able to find, you're probably not going to be on there to look for your passives, but you'll be on there to look for like fancier LEDs and all the other more cool add-ons you can add to your mouse.
Oh, also a little bit about this, like during winter quarter when we actually like get all the PCB designs from you guys. The reason we're talking about the bill of materials is because we're going to require you guys to give us a bill of materials. Basically, that tells us like what you guys actually need, and then like it'll have like all the links like buying stuff, and then we'll go more in detail in the assignments. But like this is just like we're talking about that design phase and like what we expect from you guys. But yeah, we'll walk you guys through it once we get to winter quarter. And then yeah, so that's like a little bit about like looking through the vendors and then making bill of materials. Now we're going to talk about looking at data sheets. I know some of you guys had a little bit of questions about this, like how we choose like certain things, like, why we're choosing the parts we do, and then I'm going to try to go a little bit into that here. So basically, a data sheet is like
it's like a PDF that's usually along each part that you find on a vendor site. They actually include like the data sheet like close to the top of the page, which tells you everything you need to know about the part, from like operating temperatures to like niche facts to just applications and like circuit setups.
Yeah, so when a manufacturer makes a part, they fill up this data sheet with like it can even be like tens of like, I've seen a data sheet be like hundreds of pages before. It's like everything that like a working manufacturing engineer needs to know to actually use this part. So it has everything. But then we don't want to read like 100 pages of useless information for us. So basically, this like goes over the main things that we're looking for when we're looking at a data sheet. We have the main specs, that's usually page number 1, and then pin descriptions. That's how we know like what each pin on the thing does, and then like their functions. Like we know like like if we need to use all the pins, and then recommended circuit setups. Like remember when we were setting up like the voltage regulator, for example, and then we use like those ceramic capacitors as like decoupling capacitors. How did we actually choose which capacitors to use? We didn't. We followed the data sheet, and that gave us recommended circuit setups for those actual capacitors. It's like, this is how I get by with not actually knowing much electrical like circuits knowledge. I just follow what they tell me to do. And then package description, that just tells you like what the actual like physical IC package will look like. For example, like the H-bridge that you guys have, like that's called like I think it's the dual inline package, like the one that you can actually plug into the 8-pin.
I believe that one's like a HOT6B, but I could be wrong. That might be the surface mount equivalent of it. But
well, yeah,
it just kind of tells you what form factor it comes in.
Yeah, and that's important for like the actual PCB design because it will have to match the PCB part will actually have to match that form factor. So yeah. That being said, I'm gonna go through like if I was like finding a gyroscope on Digikey, what I would actually do to see if this has the right things. It's like I found this link to this gyroscope, to a gyroscope data sheet, and then we're just gonna look through. First of all, just looking like first page specs, the pins, and then the example circuit setup. So, okay, we're going to go here. Okay, so this is going to be a, I'm not reading that part number, but this is an example of a gyroscope that I actually have on my mouse that I designed for like last summer. And then let's look at the basic data. This runs on 2.7 volts to 3.6 volts, which fits perfectly with our 3.3 volts that our microcontroller runs at. This is like temperature, and then this just talks about like some of its features. We don't really care about that. Apparently it's used in gaming, that's cool, I guess. And then, okay, so that's all we have for like first page specs. Now let's go to pin description. And in this, to be honest, doesn't tell us a whole lot. It just tells us like graphically what we, like what each of these pins are, and then like the abbreviation acronyms for the names and stuff. But then it should have right here, this will actually tell us what each of these things do. Let's see if I cannot get both of them. So yeah, basically, you don't need to know, right? If some of these things don't make sense to you, they do. A lot of times they do explain it further in the data sheet. We're not going to get too far into it, but I just want to get the idea into your guys' head that like, oh, this is how you actually see like which of these pins like this IC has and what are their functions. And then after that, this just more information. I tend to skim through a lot of this. Oh yeah, and then this is what I was talking about, the example circuit setup. So we have, if we look at this here, we have our power supply. This just represents like, LDL is a type of linear voltage regulator. It's called a linear dropout regulator. Not important. This is basically just saying like, we have a regulated 3.3 volt power supply, and then we ignore everything here. And then this is our actual circuit that we are looking to set up. Basically, analog circuit stuff, something filter, something. If you want more in-depth, we don't actually teach analog circuits in this program. That's why I'm able to say stuff like this. But if you wanted to get more in-depth, I definitely recommend like asking officers who have more experience and have actually taken these circuits classes. But for all we need to know is like for stable operations of this, you should be good with like following this circuit setup. And with that being said, okay, yeah. That being said, we have, this is a screenshot that I took of the data sheet, and then we're just gonna see, keep in mind, remember, we have this pin going to, in parallel, a capacitor, another capacitor, and then that capacitor being series with the resistor while going to ground. And then I have that same circuit setup in my schematic for my mouse. You can see, don't worry about these.
It's like right here.
Yeah, so capacitor to capacitor, and then another resistor set up in series with that capacitor, all going to ground.
This is one of the few times where we encourage plagiarism.
Yeah. And then these two capacitors, if you're curious, these are just simple decoupling capacitors that my good friend Caden suggested that I add. I don't know why. Basically like to regulate the power supply, just like we've been doing with like the linear voltage regulator and the H bridge. Some ideas. You just want to use these capacitance. If you ever need help like picking parts, picking values, just ask an officer. They'll most likely be able to help. Yeah. And then so that was a gyroscope, just like a random IC. But for the bulk of like designing your schematic in winter quarter, you'll spend a lot of time looking at the microcontroller data sheet because that has 64 pins, each with their own like unique functions and stuff. If you ever use like Arduinos and stuff, just imagine like all like the I/O pins, like all the special functions. It has basically like 3 times that. So then now we're just gonna take a sneak peek at what looking at the microcontroller data sheet will look like. Just like what you need to pay attention to. We got first page specs, choosing pins, and then examining package orientation. So yeah, do that one real quick. Is everybody following so far, by the way? Yeah. Okay. Okay. So lots of high-level information here. These are the STM32F205s. That's just what you get when you Google them. They have 17 timer channels, three analog to digital converters, which is what you guys use to grab the data from your analog, like the analog signals from your IR receivers, and like conform it into a digital format. That's why it's called analog to digital converter. And then let's see, we have a bunch of flash, a bunch of stuff, all of this jazz. Yeah, you guys don't need to worry about this because we chose these microcontrollers specifically so that they would have like enough features and enough pins that if you guys want to expand and do more with it using these extra features, you can. Otherwise, you can just leave it. Alright, so those are first page specs, and then the rest we're looking at. Choosing pins. Oh, yeah, this is a lot of fun.
You'll spend
and
a
also
lot
pin
of
descriptions.
You'll probably spend a lot of time on this page, and please do spend a fair amount of time on this page because
Yeah,
we have
so these are all 64 of our pins. You can see all the names and stuff. This will just give you an idea. This is going to be a lot of fun to solder, by the way, because you're going to be soldering these by hand. But yeah, so we have a bunch of these microcontrollers. They look like this, and then right under this, well, not directly right under. Oh yeah, this page will tell you all about what each of these pins do. So notice that before I scroll down, it has like this one. That's the 176 pin version, 144, and 100. We're not using those. We're using the small baby version, but.
You can just tell, like for example, we're using the LQFP64 package tag, so it's just over here.
Yeah.
It tells you correspondingly which pins, like has like a certain pin name in the software and all that.
Mm-hmm. Yeah. So notice that a lot of these for this column have dashes. That's because the 64 pin version of that microcontroller does not have that pin. So then like let's just say like we're looking at PC13. It has it's GPIO or input output capable, aka we can just like run it using the basic like IO functions that we've learned. And then also we can see PC13 that should correspond to pin 2 PC13 plus this extra stuff that we don't care about. But so yeah, basically what we're looking for here is like a few things. We want to know like which pins are like timer compatible. Like this one has like timer 2. So like, we need timers like motors and encoders. You guys remember setting those up. And then we also need ADC pins, which I'm going to do a quick Control F right here to hopefully find them. Oh, that's 130. All right. I remember. Oh, perfect. Let's find one that yeah. Okay. So we can see here that pins 8, 9, 10, and 11 all have ADC pins, and then we can connect multiple. All of our analog or all of our IR receivers to one analog to digital converter. So we can so like these are good enough, and then we can pick these pins as our analog to digital pins that we connect our PCB traces to from the IR receiver circuit to our actual microcontroller. So yeah, like timers, I/O pins, analog to digital converters. Megan, am I missing anything? You anything?
It's just there are certain timers that have like a specific use. Like you remember setting up like for encoder mode, but that's just more like something you need to be aware of while you're designing and picking out pins. But we don't need to go into that detail for now.
Yeah. Also, for some of you who might have some more experience, want to do some more advanced things, there's also like the I2C pins and the UART pins. I believe there's also SPI pins. Those are for if you want to add like extra peripherals like LCD display, a extra gyroscope that uses I2C, a Bluetooth module. So yeah, those are things to keep in mind. Obviously, if you don't know anything that I just said, don't worry about it. That's more just like if you want to go more advanced. Yeah, Justin.
So basically, I2C is like advanced.
It's a separate communication protocol, and it's used in like several like more like additional stuff you can add to your mouse. It's just more for it's a lot more for like communications towards like Bluetooth modules, for example. That's like it's something that you could additionally look into, but it's not required.
Yeah, I will correct. It's usually not used for Bluetooth modules. It's usually used for things like gyroscopes, LCD displays, some other stuff, and then Bluetooth modules usually use UART. But we will go over this more in the assignment, like some additional superpowers that you can add to your board. But yeah, just know that these things are there. This is how you actually parse through the data sheet and look at what pins are compatible with like what features. And then, oh yeah, one last thing. Actually, I'm gonna skip because we're short on time right now. I'm going to skip examining package orientation, which know at the end of towards the end of the data sheet, it will show you actually like which pin is which. Like the microcontroller has like a circle on it, so you can tell where
like what direction it's oriented while you're soldering it on.
Yeah, but like it's not too hard. So yeah, that is microcontroller data sheet that you guys will be looking at. Okay, how did I go up here? Okay. Oh yeah, this is what I just talked about. Timer channels, GPIOs. Make sure to look out for this when you're doing encoder channels, because encoder channels are specific timer channels. Like only some of them can use it, and like they have like different rules. It's kind of annoying, but yeah, just
read the data sheet and you'll be fine.
Yeah.
Okay, and honestly, I will just go into a quick recap and just basic parts that you need for a rat, and you guys can expand upon that, but here's just the bare minimums of what you need. And yeah, so microcontroller, the brains of your whole thing. You have like your batteries as your power, your H-bridge to power everything else at the regulated 3.3 V. Well, encoders pass everything back to the microcontroller into the encoder counts. You have you send signal up to the IR emitters, which are read by the receivers, fed back into the microcontroller, and you have the voltage regulator just kind of passing everything at a regulated voltage and all that.
Yeah, hopefully this all sounds familiar to you, and then these are the actual circuits that you will make in your schematic. You've already made a good chunk of these because like just working through the
Hopefully
assignments.
these sound familiar. At least these few should already be assignments you've already done. Like we'll ask you guys to modify some of it, but just in general, it shouldn't be that much work. I mean, it shouldn't be that much work to just add them into what you will need for next quarter.
Yes, then making your mouse schematic will just consist of like editing your previously made individual schematics and then combining them all together with the microcontroller, and then adding like buttons, LEDs, programming headers, everything you need in between. But yeah, we should be able to cover that, and then also we have like you guys have access to the RAT PCB. It's like feel free if you're like getting very lost, just like look at how we like connected things there. All right, and then just a little bit on design choices and tips and stuff we have. Yeah, if you sit down and like start staring at the assignment and have no idea what to do, Kaden and Jessica's like very nice PCB design workshop will help a lot with that. I talked about like making schematics and doing all that, and then also that should be on the YouTube channel. And then what I said, the RAT schematic is there. Oh yeah, and then so you will actually be picking pins to like connect things to, like this is what you use the labels for that we're talking about in the assignments. Like this is like the best example of like when to use a label. So like just like connect a microcontroller pin to a label, and then on the other side of your schematic, like connect another label with the same name. And then so yeah, that. Oh, and then make sure in STM32Cube IDE, like you set up a new project to like actually make sure all these pins functionally work, like that you actually pick. And then yeah, and pay attention to encoder mode, because that's the
This
biggest
is
headache.
like, the big thing is just make sure you set everything up. You don't have to write the code. Just set all your pins up as you did in your graph. And yeah, and we actually have reasons why you have to make sure,
Yeah.
or you end up with something like this.
Yeah, so a little bit of background. This is our mouse last year. We chose the wrong pins for the encoder mode. We chose timer channels that weren't compatible. So we had to solder wires directly to the pins, to the correct pins, all the way to our encoder headers. So yeah,
And
try
you
to
guys-
avoid that.
You guys have seen how small the microcontroller on your Nucleus are. They're the same size here. Imagine how much of a pain it is to solder it on. So just, word of warning, please don't have to please don't do this so you don't have to do corrective action like this.
Yeah, this is one of my favorite ones though, because this was IEEE president from like 4 years ago.
He
I
also
think
won
he chose
Micromouse.
completely wrong pins, so then he had to like lift it up, like solder everything directly, and I just really like this. We still have this PCB in the lab.
Former Micromouse lead.
It's
And
inspiring.
former
in a way.
AAA president. It's inspiring.
Okay, yeah, and then this is a little bit more PCB design. I don't know if Caden talked about this during the PCB design workshop. This is just my personal recommendation. We talked about like setting grid size in one of the assignments. For when you're actually doing the PCB part, like the board layout, set your grid to 50 mils when actually initially placing parts, just that it's like spaced out nicely, it's like everything's aligned, and then you can go to like smaller grid size if you want to go like even finer than that. Leave 30 mils of space between parts, that's just so that it's easy to solder. Do thicker traces for analog signals because like those are important. We need like signal integrity, and then even thicker traces for power, just because like if you have thin traces for power, that means that a lot of it the traces will have more resistance, so we're going to burn up extra power when the power runs through those traces. And then these 2 points, the assignments do talk about more, so don't worry too much about it, but just like keep that in mind. Oh yeah, so don't cut up ground planes too much. I'll show you what this means in the next slide, and then make it.
And it's just like we want you to separate your ground. And I know we said don't cut up your ground planes too much, but we recommend that you create a separate ground plane, because ground plane is specifically for motor related activities, because motors can generate noise. That messes with our analog data, which is bad. That messes with our readings, which is also bad. And yeah, avoid sharp turns in your traces, like with 45-degree turn. Like set them to like 45-degree turns. Because one thing space, other thing electrical engineering reasons that I won't elaborate on for the moment. And yeah, center of gravity will matter.
All right.
Trust.
And then here, this is an example of what a bad PCB board looks like. We got 90-degree traces. This just goes here for no reason. And then also, notice the polygon that we have around here. That is a ground. This is a ground polygon. So like, imagine just like this filled in with ground all the way here. I could fill it in this thing, then it just looked really ugly. But yeah, so we have our ground right here. This is the ground of our battery. And then through this ground plane, it is connected to here, this ground, and then this ground. But you see, we have a VCC trace going all the way along here. So ground can't actually go, the ground can't actually go through here. It has to go along these channels, which is bad. That's what we mean by cutting up your ground trace, or your ground plane, because like, the whole point of the ground plane is that like, it will immediately go to ground like through the fastest way possible, but like, and like along the biggest area possible. And then, but ground here, it has to travel all the way here, and then here, along this narrow path, all the way to here. And that is bad for electrical reasons that I can't explain.
And we don't have the time to explain at the moment anyways.
Yeah, but like that is just something to keep in mind. We will do like schematic and PCB design reviews in winter quarter, where like if something's blatantly wrong, we will tell you guys about it, ask you guys to fix it, and then by halfway through to like end of winter quarter, you guys will have completely functional PCBs that look better than this. Alright, and then some nice things to keep in mind when you're actually laying on your board. Make your programming header easy to access, because as you guys know, working through the assignments, you're gonna plug stuff into that programming header a lot. So make sure it's in an easy spot, and like there's no like batteries in the way or something. Test points, this is just like have like VCC or like 3.3 volts, just like available as like a pin or something. So to our rats, like you can easily test that with a multimeter to debug. Add switches and buttons for like user functionality, user input. That's a lot of fun. You can do like different modes, different like settings based on the inputs, and then status LEDs and maybe a buzzer would be cool too. And then these are examples of sample PCBs from last year. This is the one I made over the summer. And then, yeah, just try to have fun with it. Like, this is the most fun part about Micromouse. Also, what they will ask you a lot about in interviews, just like, oh, what was the PCB design process like? And then, yeah. So, yeah, PCBs. And then these are some finished designs. This was me and Megan's mouse from last year. We called it the Child V2 because our rat during fall rat competition was the child. This is the Among Us shaped mouse. I call him Gus. And then this is a different school's mouse. Notice they use like a smaller version of Nucleo board, like how your rats have, but also just like, I thought the design was interesting. And then this is Bradley, a senior IEEE officer who will be competing this year. This is the mouse that he made. He has it with, oh shoot. He added 2 buzzers on it that can play music and also NeoPixel rainbow LEDs. So I know he had a lot of fun, and now it's just playing Fireflies.
Yeah, so it's like he is Micromouse lead from 2 years ago. He's now the person running IdeaHacks this year.
Yeah.
Fantastic stuff.
Okay.
And,
So yeah, that's
Next
that.
slide.
Okay.
Yeah. Questions? Like, feel free to ask me or Nathan more on like any of the details, or if you have any other like electrical engineering related questions about like parts and like why PCBs need to be designed a certain way. I could try to help explain some of that. If not, ask another officer for it. It's fine.
Okay.
Yeah.
Yeah. Sorry we kind of speed ran this one. One reason is like we don't want to keep you guys here for too long because we have pizza. Other reason, there's another club. This room got double booked apparently, and they are counting on us being here in 2 minutes, being out of here in 2 minutes. So yeah, if y'all have any questions, save it for after this. Start packing up. But then also IdeaHacks.
Sign up.
We showed this last time.
Please.
Sign up. Past project. Oh yeah.
Yeah.
For our competition, week 10. Maybe.
Trying.
We'll see. We will let you guys. We will keep you guys updated. It depends how the soldering situation goes. I signed up 4A and 4B. We released them already. Do the coding part first if you don't have access to a soldering iron. We talked about that in assignments. Free pizza. And then your resistor. Yeah. Oh, one more thing. So if we don't have access to soldering irons and aren't able to solder for assignment 4, then we will push back the fall rack competition to week 1 of winter, most likely, and then we will just have you guys start working on the mouse designs early, which is why we had this lecture. Yeah.
All right.
All right. Thank you guys for coming.
Guys.